Okay, so this is setting up 6.11. What we're going to try to do is we're going to try to take a minimization problem, say in standard form, and we're going to try to put it into tableau form, and then we're going to try to figure out a way of solving it using a simplex method directly without having to go through big M or two-phase. So just as an example, how we normally would solve it, we would convert this min into a max by negating the W. Then we would go ahead and plug it into our tableau. And now we were stuck here, right? Because for one thing, row 0 is all positive. And then we don't have columns of the identity, which is a problem because simplex method requires a basic feasible solution to start. And so how should we proceed? Well, the idea behind big M and two-phase was to introduce the artificial variables, and that gave us columns of the identity. But let's see if we can do something different. What happens if we negate the two rows? Um, what we have here then, if we interpret this correctly, is y1 equals 0, y2 equals 0, y3 equals 0, e1 is equal to minus 4, and e2 is minus 6. So what kind of a solution is that? That is a basic solution because we have the zeros in there, but it's not feasible because E1 and E2 are negative. Okay. Um, However, this is very similar to another tableau that we're going to look at. And so let's, instead of doing this directly, let's think about what the dual actually is for this problem. So if I go back to my original problem and I construct the dual, I get this problem. If I set up the tableau for the dual, it's going to look similar to the tableau, right, for the primal. And let's compare the two. And so here we have like a 1, 2, 0 here, corresponds to 1, 2, 0 here. The minus 4 and minus 6 in the right side of my minimization problem corresponds to this. Now this is interesting, and this is actually why we multiplied these by -1, because we end up with this nice relationship here between these two. Okay, so now if you inspect this tableau to the right, you'll see that we are in the right form now for the dual simplex, or the simplex method on the dual, right? So this was the dual, right? And this is the, if we do the simplex method here, we can oh yeah, this is just saying sorry, the tableau on the right, we do have a basic feasible solution, right? X1 and X2 are equal to 0, and then the S's are the 1, 2, and 0. And the tableau on the left, we have a basic solution, but it's not feasible, right? So the idea is that I can perform the dual, sorry, I keep saying the dual because we're going to be doing the dual simplex method. We can do the simplex method on the dual, this tableau right here, and see how that affects, or what that would mean if we were to perform the exact same operations on this minimum tableau directly. Okay, that sounded a little bit confusing. Let's go ahead and just see what I mean by that. So let's just go to our normal routine here. This is our tableau that was ready for the simplex method. We start by taking the, or by finding the row 0 value with most negative number, and then we continue by taking the ratio test. So that's 1/2, or 2 versus 1, 2 over 1, or 0 over -1. That one we ignore, that one, right, because of the -1. We don't ignore it because of the 0, right? We could have done that. If this had been a positive one, we would have included that in our computation. Okay, so that means the 2 here is our pivot, and let's see what that corresponds to in terms of our dual, in terms of the minimization tableau directly. So instead of looking at the -6 in row 0, what we could have done in the original tableau is we could have looked to the right hand side and looked for the biggest negative value on the right hand side. And notice that we're going to be doing something similar to this row as that we do to this column. So the idea here is that you're going to be looking at the negative values now instead of the positive. And then we'll do the ratio test between row 0 and this row, then highlighted in red. So in this case we would have 1 over negative 2, take the absolute value. That'd be 1/2. Or 2 over negative 1, take the absolute value, that'd be 2. And then these 3 we ignore. Notice that that corresponds to over here taking 1 over 2 and 2 over 1. Okay, so therefore we only look for the negative values in this highlighted row, and those are the ones that we're going to use for the ratio test. Okay, and so in this case, if we do that, we find that we're going to pivot on the same, well, kind of the same value there, the transpose of the same value. So now we're going to be pivoting here at on this -2. So notice that this entry, by the way, is the 2-1 entry, and this entry over here is the 1-2 entry, right? So you're just flipping the entries. Good. And then we'll go ahead and pivot in both tableau and see what we get. So let's go ahead and pivot. And here we pivoted here we pivoted here. Are we done yet? Nope. But we can get the current basic solution, right? X1 is 0, X2 is 1/2, S1 is 0, S2 is 3/2, S3 is 1/2. Right? And similarly over here, we can get the current basic solution. Y1 is 3, Y2 is 0, Y3 is 0. E1 is -1, E2 is 0, so this is still not a feasible solution, right? And this is feasible, but it's not optimal. Okay, and so what are we going to do next? Well, we're not finished with the simplex method yet, because we still have this -1 in row 0 over here. And notice again, coming over to the right hand side over here, that corresponds to this -1. Okay, and so because we have a negative on the right hand side of our min problem, we can go ahead and perform the row reduction on this, something on this row. We'll have to figure out which one to pivot on. Which ones are we going to compute the ratio test on? Well, it'll be this 3/2 here and this -1/2 here, right? We're going to ignore the other values because they're positive or 0. Okay, so we're going to have 1/2 divided by -3/2, take that an absolute value. 1/2 divided by -1/2, take that an absolute value. Notice that that's corresponding to what? 1/2 divided by 1/2, 1/2 divided by 3/2, right? We're getting the same, that same relationship there. Okay, so let's go ahead and do that. So we'll do that one more time. I'm going to review just a second. Good, so we're taking this column, which corresponds to taking this row, and now we perform the ratio test, and the ratio test tells us which one is going to be the pivot. The 3/2 is going to be the pivot. Good, and so that corresponds to this 3/2 being the pivot, or -3/2 being the pivot. Very good. And so if we pivot on both of those, what do we get? Now we're looking up, because on the left we see an optimal feasible solution, and on the right we also see an optimal feasible solution. Good. And so what are these solutions? Y1 is going to be 10/3, 0, 2/3, 0, 0, feasible and optimal. And on the right hand side here, that's the left. X1 and X2 are 1/3, right? And then we get the slack variables. S1 is 0, S2 is 7/3, S3 is 0. Good. And now both of the original and the right hand side are now feasible. Now notice, by the way, that because we negated row 0, right, the minimum problem does not have a value of -10/3 as its optimal value, right? It's actually positive 10/3. Okay, so be sure and we want to be sure and interpret the end result correctly. Okay, so this is the optimal tableau for the min problem, where the optimal value is actually positive 10/3. Very good. And so now just a couple of notes. When we started, we were given a min, we converted to a max, and then we constructed the tableau. Now notice when we did that, we're going to assume that row 0 is greater than or equal to 0. I wonder why. And so just to remind you what we were looking at before, we had this 1, 2, 0 here. Where did it go in the original max problem? Well, for the max problem, it goes on the right hand side. Notice what happens if you have negative values up here in row 0. What does that do to your dual? Oh, it's not going to be good for your dual, right? Because you're going to end up having negative values on your right hand side. Okay, so we're going to assume that our initial tableau has all greater than or equal to 0 constraints. Okay, now there is a way of making that happen if you don't have it originally, but we're going to just assume that in order to use what we're going to call the dual simplex method, we have all positive values up here. Okay, and then this is why, because we want a feasible solution for the max problem. Good. And now also when we were performing the ratio test, we did something weird. We were only using the negative values in that row instead of the positive values, right? And so what if there are no negative values that we can use? That's the question. Now what happens in the primal? So let's take a look. For example, what would happen if we had a situation like this where we have all positive numbers here, and so the ratio test fails? Well, that means that the problem is infeasible, because your y1 and y2, y3 are all positive, greater than or equal to 0. You can't sum a bunch of positive numbers together and get a negative number. And so therefore this is infeasible. And this makes sense, because if the ratio test fails in the primal, right, that meant we had an unbounded solution. But if it fails in the dual, we get an infeasible solution. Good. And so we're going to construct the dual simplex method in just a second, but I'm going to stop this video here, and we'll start over again in just a minute.